In the incredibly complex world of industrial engineering, what's the one thing that stands between a totally normal day and an absolute catastrophe? Well, a lot of the time, it's just one simple, brilliant device that has to work perfectly, every single time.
And this is what's at stake. Mexico City, 1984. This is a horrifying reminder of the immense power that we try to contain, and what happens when that containment fails. This is the absolute worst-case scenario. This is what all that engineering is trying to prevent. So, okay, how do we prevent something like that? Well, we rely on a true unsung hero of the industrial world, a device that acts as the final guardian, the last line of defense against a system getting dangerously overpressured.
The easiest way to get your head around it is to just picture the little whistling valve on a kitchen pressure cooker, right? It lets off steam when things get a little too intense. Okay, now imagine that same basic idea, but scaled up, way up to protect a chemical reactor or a refinery column that's the size of a building. That, my friends, is a pressure safety valve, or a PSV for short.
So here's the official definition. But the key words you really got to focus on are self-actuating. This thing needs no computers, no electricity, no human to flip a switch. It just works on pure physics. It opens up to save the day, and just as important, it closes again to stop whatever's inside from completely emptying out.
And the principle behind it is just beautifully simple. You've got a spring, and it's been calibrated with incredible precision, holding a disc shut over an opening. As soon as the pressure inside that vessel builds up and pushes harder than the spring, pop! The disc lifts and all that excess pressure vents out safely. It's just mechanical elegance at its finest. But knowing what a PSV is, that's the easy part. The real challenge, the true art of the engineering here, is figuring out exactly what kind of valve you need and what it needs to be ready for. It's all about planning for the absolute worst. And I just love this quote. The job of a process safety engineer is to be a professional pessimist. Their entire career is basically built on looking at a perfectly functional, happy system and asking, all right, how could this thing fail in the most spectacular way possible? And that pessimism, it gets channeled into this really rigorous, methodical process. It is not guesswork. First, you figure out where the valve needs to go. Then, the engineers literally brainstorm every single thing that could possibly go wrong. For each of those disasters, they calculate exactly how much pressure it would create. And then finally, they pick the single worst, most terrible outcome, and they design the valve to handle that. And just look at the list of potential disasters they have to think about. I mean, we're talking about everything from a fire starting outside the tank to a total plant-wide power failure, a simple blocked pipe, or a critical cooling system just given up. Every single one presents a totally unique challenge. Now, to keep from being completely paralyzed by infinite possibilities, engineers use a critical rule of thumb called double jeopardy. They have to design for any single thing to go wrong, but they don't assume two unrelated things, like say a fire and a power failure, are going to happen at the exact same moment. It's a key assumption that makes designing for safety even possible.
All right, so let's walk through a couple of these high-stakes what-if scenarios. This is where all that theory gets put to the test in a trial by fire. And by failure.
Okay, scenario 1, an external fire. Just imagine a flammable liquid has leaked. It's formed a pool right around the base of a huge pressure vessel, and whoosh, it ignites. That fire immediately starts to heat the walls of the vessel and everything inside it. So that heat, it starts boiling the liquid inside, which generates a massive amount of vapor, and the pressure starts shooting up. But, and this is so important, as this table shows, the outcome changes dramatically depending on how the vessel is protected. A bare vessel with bad drainage, it absorbs a ton of heat. But if you have good drainage, so the burning fuel can flow away, it's better. And if that vessel is properly insulated, the heat absorbed is incredibly low. See? Every single design detail matters.
All right, now for scenario number 2, a total power failure. In a lot of industrial plants, this is the single most demanding event the safety systems could ever face. It's often the one scenario that dictates the size of the entire relief system for the whole plant.
And this kind of failure is especially dangerous in a complex piece of equipment, something like a fractionation column you'd find in a refinery. It's basically a huge, tall tower with heat going in at the bottom and cooling happening up at the top. A power failure here, well, it can set off a pretty terrifying chain reaction.
It all starts with this one single event, a sudden, total loss of electrical power to the whole facility. Instantly,
Every single piece of electrical equipment goes dead. The pumps pushing cooling water around, the giant fans on the air coolers, the system's entire ability to get rid of heat is just gone.
But, and here's the kicker, the heat sources, especially the ones that run on steam, they don't need electricity. So they just keep on chugging, pumping heat into the bottom of the column.
So now you have this critical imbalance. Heat is just pouring in, but absolutely none is getting out. The liquid inside starts to boil uncontrollably, and the pressure starts to climb and climb fast.
And in that moment, with every other system completely offline, that one pressure safety valve is the only thing standing between the system and a rupture. It becomes the single, final escape route for all of that immense building pressure. So when you pull all of this together, it paints a really clear picture, doesn't it? The PSV, it's not just a piece of hardware. It actually represents an entire philosophy. It really is engineering's last defense. And this is the main takeaway here. The safety we so often take for granted in our highly technical world, it doesn't just happen by chance. It is not an accident.
It is the end result of countless hours of rigorous, pessimistic, and, let's be honest, absolutely brilliant engineering design. It exists because it's somebody's job to imagine the worst possible day and then design a clever solution so that the rest of us never have to live through it. And that really makes you think, doesn't it? What other invisible safety systems are all around us, quietly doing their job, protecting you every single day?